So as we mentioned, the domain of a relation is the set of all inputs, and in an ordered pair xy, our default is that x is the input and y is the output. Which means that the domain is now really the same thing as saying the set of all x values. If we're looking at a graph like we have here, then the domain is going to be the set of all numbers that serve as an x-coordinate of some point on the graph. So if we start by labeling coordinates, this one is -4, -3. This one here is -3, 0. Up here we have -1, 4. Down here we have 0, -2, and over here we have 2, 0. What we're going to do is list all of the numbers that are an x-coordinate of one of those points. So first we have, if we work from left to right, it'll be easiest. First we have -4. I'm going to put these in set braces. Next we have -3. Next we have -1. And then 0, finally followed by 2. So our domain is the list of all values that serve as the x-coordinate of one of these ordered pairs. The range is going to be all values that serve as the y-coordinate of one of these ordered pairs. So from our first point that we used for the domain, we have a y value of -3. So -3. Next we have a y value of 0. Next a y value of 4. Next we have a y value of -2. And finally we see another 0. We don't list that 0 twice. A set should never have an element listed more than once. Sometimes it can be helpful to put the numbers in order, in increasing order, just to make sure that you won't accidentally write the same element twice, but it's not necessary that they be listed in numeric order. So one thing that made this problem a little bit easier than some is the fact that it's really, both of these were finite sets. It was possible to simply list the elements in each set. On this next graph, because it's continuous, we see that it starts at one point and then we have a solid line all the way to another point. This is an infinite graph. The graph actually has an infinite number of points that connect the starting point with the ending point. And it really comes down to how finely we're willing to look at it. For example, it doesn't just have -3 as an x value and -2, it also has -2.5. It also has numbers like -2.179326. So if you're willing to let that decimal representation go out far enough, you're always going to be able to find another point that you haven't already listed. So we cannot list the values in the domain here. This is going to be an infinite set, and therefore we're going to need to use a different kind of notation here. Set builder notation and interval notation would be the most common kinds of notation to use to describe this domain. So what we want to do first is figure out what our set is. The set is going to be all x values that serve as the x-coordinate of some point on the graph. So what we want to do here is try and examine it for a smallest x value. It does have a left endpoint right here, and if I trace up to the x-axis, I can see that that left endpoint occurs at x equals -3. It also has a right endpoint on the graph, and if I trace down to the x-axis, I can see that that right endpoint occurs at +5. Furthermore, since the graph has no breaks in it, I can see that all of the numbers that are between -3 and +5 also correspond to some point on that graph. So what I want to describe here is some sort of reasonable notation for all values between -3 and 5. There are two ways to do this. One way would be using an inequality statement in set builder notation. We can say the set of all x such that -3 is less than or equal to x, which is less than or equal to 5, and then close off this set notation. Another way that we can do this is using interval notation, so I'll squeeze that answer in here as well. This would be with square brackets -3, 5. Both of these notations are fairly common ways to express this set. One thing that is very important if you're using the inequality statement, in a statement like this with two inequality symbols, they need to always point the same direction. It's a fairly common mistake for a student who's just learning to use these statements to make them both open toward the x, for example. And if we read this, one way that we can make sure we're reading it correctly is to make sure that we always read from the variable. If I read from the variable, starting with the second half of the statement, it says x is less than or equal to 5. And that's fine. We see that x is, that the graph we have up here is to the left of 5. If we then look at the first half of this statement, -3 is less than or equal to x, reading that from the x backwards, that says x is greater than or equal to -3, which is in fact what we have here, that it goes to the right of -3. So having the inequality symbols point in the same direction is always what we want to state that x is between two values. Now we're ready to look at the range. Similarly to what we did with the domain, we now want to find a smallest and a largest y value on the graph. It looks like our smallest y value again comes from an endpoint, and our smallest y value here is -4. Our largest y value, this can be a little bit tricky because sometimes people go straight for the endpoint, since the endpoint was what worked for domain. But in fact, the endpoint does not give us our largest y value. We can see that the top of this hill here is actually the highest point on the graph, and therefore our largest y value. So for our range, we want to go between -4 and +4, and again we're going to use either set builder or interval notation to express that. In this case, our set builder notation, we would use the y variable, the set of all y, such that -4 is less than or equal to y, which is less than or equal to 4, or an interval notation indicating that it's all values between -4 and +4. These brackets really mean that it's an interval, not just the two values -4 and +4. One thing I want to emphasize before going on to the next example is that it is not possible to express these infinite sets the same way that we expressed these examples over here, where all we had to do was list numbers. This only works for finite sets. It can sometimes work for infinite sets if a pattern can be established, but not for the kind of continuous infinite sets that we see in this example here. So we absolutely have to change our notation to express the domain and range in these continuous graphs. All right, this will be a very similar concept to what we just did. The main thing that makes this one a little different is that we now have an arrow on the end, so we're not necessarily going to be able to find a smallest and a largest x and or y value. But the idea will be the same. Let's start with the domain. We look to see if we have a smallest x value. One way that we can think about what we're doing is that we are bringing in a vertical line or the edge of some sort of rectangle here and moving it gradually to the right until we hit the graph. And the first point at which we hit the graph, we can go ahead and see what was that x value. I can see here that x value is -4, so I'm going to go ahead and identify that -4 as my smallest x value. As I try the same thing from the right, I'm moving over till I hit the graph, and I see I hit the graph, but I hit an arrow, and that arrow bounces my rectangle back. So that tells me I don't have an upper bound, and I'm going to instead want to use an upper bound of infinity here. So that means that my domain has a smallest value of -4 and a largest value of infinity. There are a few different ways to write this set. We can, following the same model we followed previously, start with that set builder notation and beginning with our left endpoint, -4 is less than or equal to x, which is less than infinity. However, it's not really necessary to state that x is less than infinity. That's kind of implied. So we could also use set builder notation, just simply stating it's the set of all x such that x is greater than or equal to -4. Sometimes people will automatically just gravitate towards one of these statements or the other. Both of them correspond to the set that starts at -4 and continues off to the right to positive infinity. Writing this same thing in interval notation would simply look like square bracket -4, comma, infinity. This section is not really intended to teach interval notation. That is generally covered with other topics, so if interval notation is not something that's totally comfortable with you, just pick the one of these that you do know. Now we're going to do a similar thing with the range. We're going to take this rectangle again, and this time we're going to move it up from the bottom, approaching the graph, and again we see that we hit an arrow right away. That arrow pushes us back down. This time we are not going to positive infinity, we're pushed in the downward direction, which really would be toward negative infinity. So negative infinity is going to be the lower bound for our range. When we then try grabbing this rectangle and bringing it down on the graph from above, we see that we hit the graph at 3 and we hit it in a solid point. So that tells us that y equals 3 is the upper bound of our range. So I'm going to take that 3 solid dot, downward arrow to negative infinity. When I write my range, this is the set of all y such that negative infinity, always start with the smaller number if we're doing these less than symbols, is less than or equal to x, which is less than or equal to positive 3. Or we could simply state the set of all y such that y is less than or equal to 3, again, leaving out the statement that, sorry, that was supposed to be a y here, leaving out the statement that y is greater than negative infinity, which is sort of implied. Or we could simply state the interval from negative infinity to positive 3 with a square bracket on the 3 and a round parenthesis on the negative infinity.